Hello, in this podcast we're going to talk about hypothesis testing. And in particular we're going to talk about the theory. So what we aren't going to do today is to introduce a whole range of different statistical techniques. We're going to focus on one particular hypothesis test and look at some of the underlying theory. And in addition to doing that, we're going to finish off what we do in this podcast by talking about, very briefly, power and sample size calculations. So we're going to begin by assuming that we have a data set of size n. So n is our sample size, and we have n observations, and they're made on a random sample. And we're going to denote these observations as x1, x2, up to xn. So we're using the capital letter X to denote an observation on, if you like, the xi would be an observation on the ith individual. Now, we're going to assume a statistical model for these observations, and in particular we're going to assume that xi is normally distributed with mean mu and variance sigma squared, and of course I is going to go from 1 up to n, and we're going to assume that the observations are independent. So this means that the normal distribution takes the following shape, the bell shape that we've met before. So here we have the values that x can take. Here we have the shape of the normal distribution, looking like this. This is the probability density function. And this would often be denoted f, capital X as a subscript little x. So a capital letter is used for the random variable and a little letter is used for the value it takes, but we won't worry about that too much today. And the width of this at a certain point is sigma, and it's centered on mu. And values occur according to this probability density function, so that values near the center occur more often than values out in the tail. So the dots, the crosses there on the axis could be thought of as our n data points. Okay, so throughout this we're going to assume that sigma or sigma squared is known, and we're going to assume that mu, the mean here, the location of this distribution, is unknown, and we want to perform inference about mu. Now, what do I mean by perform inference about? Well, that really means, in a simpler language, to learn about. So we want to learn about the unknown parameter mu, and we want to learn about that from the data. So the data are x1 up to xn, observations on the random sample of size n, and that is going to tell us something about the parameter mu. As I mentioned, we're going to, for now, assume that the parameter sigma is known, so we aren't going to be worried about estimating the parameter sigma. So, before we go any further, we're going to take a short pause, in a way, from our discussion of hypothesis testing to discuss some properties of the sample mean. So the sample mean is often denoted x bar, and we get the sample mean by adding up all the values. So that's the sum I equals 1 to n of xi, and dividing by n. So that's the definition of the sample mean. And we're going to work with the sample mean a lot. Now the sample mean is a sum, and then we divide by n, but essentially it's a combination, a linear combination of normal or random variables. Remember that each xi is normal with mean mu, variance sigma squared. So because it's a linear combination of normal random variables, it's itself normal. So x bar is normally distributed. Now the normal distribution is characterized by its mean and variance. So that means we need to know the mean and the variance of x bar, and then we know the full distribution of x bar. So we're now going to work out those quantities. The mean of x bar can be worked out as we're going to do now. So that's the mean of the sum divided by n. And then probabilities of the mean tell us that we can take out a constant. So that can be written as 1 over n, the expected value of the sum. And the expected value is a linear operator, so it can be brought in through the sum. So that's 1 over n, the sum, I equals 1 to n, the expected value of xi. And we know by the assumption above that the expected value of xi is just mu. So when we add up mu n times, when we add up a constant n times, we just get n mu, and the whole thing therefore is 1 over n times by n mu, which is just mu. So the expected value of the sample mean is mu, the underlying mean of the random variable, the measure of location of its distribution. And that's a good thing as far as estimation is concerned. We know that on average the sample mean is the random variable mean. Okay, we can also work out the variance of x bar, and the calculation is more or less the same, but proceeds in a slightly different way. So that's the variance of the sum divided by n. But when we take out a constant from a variance, we have to square it. And the intuition of that is that the variance itself is a square measure. So when we take out a constant, we end up having to square that constant. So we end up with 1 over n squared, the variance of the sum. And the variance can pass through a sum, provided that the random variables are independent. That's not necessarily when we make the expected value pass through the sum. The expected value always passes through the sum, but the variance passes through the sum when we have independence. So we therefore end up with 1 over n squared, the sum, I equals 1 to n, the variance of xi, and we end up at this because the xi's are independent. And therefore a very similar argument now as before can be applied. That's sigma squared. The whole thing is n sigma squared. So we end up with the variance of the sample mean is 1 over n squared times by n sigma squared, which is sigma squared over n. So the variance of the sample mean, the spread of the sample mean, decreases as the sample size n increases. And those results together, and I'm going to put this in a box here, tell us that x bar, the sample mean, follows a normal distribution with mean mu and variance sigma squared over n. So that's a very important property of the sample mean, and we'll put that in a box, and we'll be using results like that or based on that later. Okay, so that was a discussion of sample mean. We're now going to talk about a technique called standardization. And again, this is something we're going to make use of in our discussion about hypothesis testing. We've just established that x bar follows a normal distribution with mean mu and variance sigma squared over n. And then we can subtract the mean. So what's the distribution of x bar minus mu? Well, that just means we subtract the mean from the first parameter, the mean parameter of the normal distribution. So that would have that distribution. We're effectively shifting the distribution. And mu minus mu is 0. So the distribution of x bar minus mu is normal 0 sigma squared over n. And then again, by a standard property that we saw before when we were taking out a constant and squaring it, then if we divide through by the square root of the variance, so if we divide through by sigma over root n, that will have a normal distribution with mean 0, variance sigma squared of n divided by the square of that quantity, and that will have a variance of 1. So this quantity here, x bar minus mu over sigma over root n, follows a normal distribution with mean 0 and variance 1. And again, that's a key result, and we're going to explore that a little more. First thing to say is that sigma over root n is sometimes referred to as the standard error. Of the estimate x bar. So it's the standard deviation of x bar, but when we think of it in terms of estimation, we refer to it as the standard error. And as mentioned, this technique is called standardization. So the technique was basically we subtract the mean and we divide by the standard deviation. And what we've gained by doing this is that on the distribution here on the right-hand side doesn't depend on any unknown parameters. So this does not depend on any unknown parameters. It's a standard normal distribution with mean 0 and variance or standard deviation 1. There's no unknown parameter involved there. And because of that, the quantity on this side is this random variable, x bar minus mu over sigma over root n, is known as a pivotal quantity. Now that's allowed to depend on unknown parameters. We're assuming mu is unknown, but its distribution does not depend on any unknown parameters. So that is a key result and introduction to or revision of standardization technique. At this point, it's a good idea for us to just think about what a standard normal random variable is and what it represents. So here we're going to talk about the standard normal distribution. And this distribution, again, it's the same bell-shaped curve that we've seen before. So if we represent this as Z, and if we now draw here the probability density function of Z, then it looks like a bell shape before. I'm not very good at drawing this. But this has various properties. The equation of this probability density function is 1 over root 2 pi e to the minus z squared over 2. And z takes values between minus infinity and infinity. And one of the properties of this distribution that we'll use is the number 1.64, approximately. So these tails should tail off to 0. The number 1.64 cuts off 5% in the tail. So you have a 5% cutoff with the number 1.64. That, of course, leaves 95% in the body of the distribution before the tail. So we can sometimes we write these as decimals, 0.05 or 0.95. And what this tells us is that the probability that the random variable z is less than or equal to 1.64 is 0.95, or the probability that z is greater than 1.64 is 0.05. So the interpretation of that would be that if you generated values of z at random, you get a lot more in the center than in the tails, and 5% of the generated values would be greater than 1.64, and 95% would be less than 1.64. That idea can be generalized. So here again is the same standard normal distribution, the probability density function, drawing again here, that should look the same as above. And here's z, and z is any value, and you can ask yourself, what's the probability z is less than or equal to z, little z? Well, that's the area up to little z, and that area in general cannot be found by a formula. It's denoted by the function capital phi of z, and this can be found using a computer. So the shaded area in this picture represents capital phi of z. And for example, we could find by a computer that capital phi of 1.64 is approximately 0.95. That's what we saw above. You can work out capital phi in R using the function p norm. P in this case stands for probability of normal random variable. I think it's also worth pointing out that sometimes this probability density function is denoted little phi z. So that's a discussion of the standard normal distribution that we'll be using in our discussion of hypothesis testing. So now we've got all we need to work on hypothesis testing. And in particular, we're going to motivate what we do by what I'm going to refer to as a research question. And our research question is going to be, is the value of mu greater than 3? So you'll remember that mu is the measure of location or the center of the normal distribution from which our data come. So maybe I'll draw that picture up again. So here's the distribution of the data, very badly drawn. Here's x, here's the probability density function of x. Here's mu, remembering that xi comes from a normal distribution with mean mu and variance sigma squared. And we don't know what mu is. We do, in this case, assume that we know sigma, and we're hypothesizing, or we're asking ourselves, could it be that the value of mu is greater than 3? How do we test that? How do we answer that question using data? Well, so that's what we have. We have data. So how do we answer that question using data? Well, the first thing that we should do is we should write down what's called a null and an alternative hypothesis. So the null hypothesis is often denoted H0 and the alternative is denoted H1. And what we often do is we put our research question in the alternative. So our research question would go here, mu greater than 3. And the null hypothesis would be the opposite or complement of that, mu less than or equal to 3. So please just note at this stage that we have the equality can appear in the null. So the null hypothesis allows for mu equal to 3. And we could actually draw the picture of these hypotheses along the number line. So here we have mu, here we have the value 3, and the alternative hypothesis is occupying this part of the space of the number line, because the alternative hypothesis is saying that mu can be greater than 3, whereas the null hypothesis is occupying this part of the number line, because that's saying that mu is less than or equal to 3. So what we need to do is we need to decide. We need to make a decision between the null hypothesis and the alternative hypothesis. And we're going to do that using data. And traditionally, the way that such a decision is made is based on what's called a test statistic. And the test statistic in this case is going to take a form similar to what we've seen before when we were talking about standardization. X bar minus 3 over sigma over root n. Now, note that this test statistic doesn't depend on any unknown quantities. Before, mu was unknown, but here we're putting in a value for mu, which is 3. X bar would be known from the data. It's the sample mean. We're assuming sigma is known, and n is known because it's the sample size. So this test statistic just can be worked out given the data set. And to save writing, we're going to write this test statistic sometimes as capital Z. Okay, so we have this idea of the test statistic. So we'll move on to the next page, and I'll write the test statistic at the top of the next page again. So we have Z equals X bar minus the mean 3 over sigma over root n. So 3, of course, is coming from the hypotheses. And what does this Z do for us? Well, this Z actually provides us with a measure of difference. And it's a difference between what? It's a difference between x bar and 3. Because on the top of z we have x bar minus 3. So x bar somehow quantifies in a standardized way the difference between the sample mean of the data and the hypothesized mean. Now, how does that quantification work? Well, if z, which is x bar minus 3 standardized, is large and positive, what does that mean? Then that means x bar is much bigger than 3, and that means that the data supply evidence against H naught. So what is H naught? Just let me remind you, H naught is mu is less than 3. So the data supply evidence against H naught and in favour of H1. Mu greater than 3. And the logic of that is that the sample mean is much bigger than 3, so that suggests that the underlying random variable mean will be bigger than 3. On the other hand, if z is negative, now what does that mean? Similarly, that means x bar is less than 3. And so that really means that the data do not supply evidence against H naught. That's because when you have x bar less than 3, that's suggesting that the underlying random variable mean is less than 3. Okay, so that's some sort of general idea of the use of this test statistic. It's a measure of evidence in the data against the null hypothesis in favour of the alternative hypothesis. When the test statistic is large and positive, it's suggesting H1. When the test statistic is negative, it's suggesting H naught. But that's the sort of general description. We need to quantify these ideas. And we'll now discuss how to do that. So the way we quantify what we've just said is by the following. We essentially assume the null hypothesis is true. So if the null hypothesis is true, then one possible value mu could take would be 3. You will remember that the null hypothesis is that mu is less than or equal to 3, so that 3 is a possible value under the null hypothesis. And this means that when mu equals 3, that z, the test statistic, which just let's remind ourselves what it is, follows a normal distribution. That's with mean 0 and variance 1. That's one of the results that we've seen before when we were talking about standardization. If mu is 3, then that test statistic follows a standard normal distribution. That's by our key result. And what I'm going to do to save us a lot of writing, I'm going to just put an H0 over there by saying, well, if H0 is true, if H0 holds, the null hypothesis holds, then the test statistic follows a standard normal distribution. Well, we discussed the standard normal distribution before, so let's just draw the picture of it again. So here it is. Here's possible values of the test statistic centered on 0. Here's the distribution that we denote f of z. Sometimes we denote phi of z, little phi. And what this means in practice is that if the null hypothesis is true and mu is 3, then we collect a data set, we work out the value of the test statistic, it might be here. We collect another data set, work out the value of the test statistic, it might be here, and so on. So we get a lot of potential values of the test statistic distributed according to a standard normal distribution, mean 0, variance 1, with few values in the tail and more values towards the central part. And we've seen from the previous arguments that values that are large and positive provide us with evidence against H0. So values that are in the tail, so if you calculate the value of the test statistic for a data set and it's in the tail, that's providing you with evidence against H0. So let's see a concrete example of this. Let's say that we have a data set of size 16 and that we know from a previous study that sigma is 2. And that when we calculate the sample mean for our data set of size 16, we get the value 4. Now, this means that z, the value of our test statistic, which is x bar minus 3 over sigma over root n, is going to be 4 minus 3 over 2 divided by root 16, which is 4 minus 3 over 2 over root 4, which is 1 divided by a half, which is 2. So the value of a test statistic for a data set that had sample mean 4 would be 2, and maybe 2 takes a value here out in the tail. So there's 2 in the tail. So a value such as 2, which is large and positive, certainly provides evidence against the null hypothesis. And it could be thought of as a rare event because it's in the tail somehow. We can think of the tail values as rare events. So it's a rare value of z. Okay, now with that in mind, with this idea of evidence against the null hypothesis and rare event in mind, there are two ways that we could essentially argue. So the first way that we could argue is the following. We've assumed H0 is true. What we end up with in this case is that the value of z for our data is rare. So under the assumption that the null hypothesis is true, we wouldn't expect to see a value of z such as 2 very often. So we could conclude in that case that we've been unlucky. We've just happened to have come across a rare data set leading to a rare value of the test statistic z. And that's, in a sense, perfectly fair. An alternative is to say this. Well, H0 is true. That means, under that assumption, that we have a rare z value. Well, unfortunately, that perhaps isn't a sensible way of arguing, because the only thing that we have, the only thing that we know for certain is the data. So the data are the only certain thing that we have. So, could it be that the data are rare? Well, we don't really know, but it's unlikely in a sense because the data have actually been observed. They've actually occurred. So what might go wrong in the argument, therefore, is the assumption that the null hypothesis is true. And that's the way we tend to argue when we do hypothesis testing. We assume the null hypothesis is true at the beginning. We quantify how rare the value of our test statistic is. If it's very rare, meaning that our data set is very unusual, we then go back and question our initial assumption about the null hypothesis being true, and we therefore effectively reject the null hypothesis. So that's the sort of philosophical idea behind hypothesis testing, that you look to see how rare your data are, conditional on H0 being true, and if the data turn out to be rare under that assumption, you reject that assumption. It's in a sense, in a random sense, like a proof by contradiction. Okay, so I suppose what we have to do now is we have to quantify what we mean by rare. That's going to be, again, based on a picture of the standard normal distribution. So we've drawn a lot of pictures of the standard normal distribution today, and you can see how important it is for us. So here's our, again, same picture that we've seen before. Here we've called it f of z. And we've seen that tail values correspond to rare values, and they correspond to evidence against the null hypothesis in favour of the alternative. So, how do we quantify rare? Well, one way we do it is we consider 5% of the time to be rare. So we cut off in the tail 5%. We've seen this before. Sometimes we write that as 0.05. And then our rule would be that we reject the null hypothesis if our value of the test statistic falls in the tail. And then if the value of the test statistic does not fall in the tail, in the other 95% of the distribution, we do not reject H0. So that is how we quantify rare. The region where we reject the null hypothesis is referred to as the critical region. And the value which cuts off the 5% to define the critical region is defined as the critical value. And in this case, it would be 1.64, as we've seen before. So that's a definition of what we mean by the critical region, the region of rare events where we would reject the null hypothesis. The 5% or 0.05 value to define rarity is often used, but it doesn't have to be used. We could use other values, and we aren't going to discuss that today. But we always state which value we're using, and we do that by referring to this procedure as a test of size 0.05. So a test of size 0.05. So a test that's defined in the way I've done above, you compute the value of your test statistic and you compare it against a standard normal distribution and you cut off 5% in the tail. That's referred to as a test of size 0.05. And we can ask ourselves, what's the probability of error? So we're going to talk a little bit about errors that we can make when we do hypothesis testing. One of the possible errors that we can make is we can reject the null hypothesis when it's true. So I'm going to write this line here to mean given that or when it's true. So we can reject a true null hypothesis. So this line here means when or given that. Conditional upon. And this is referred to as a type 1 error. And we can work out the probability of a type 1 error as follows. It's really quite straightforward. In this case, the probability of a type 1 error is the probability of rejecting the null hypothesis. Well, when would you reject the null hypothesis? Well, you reject hypothesis if the value of your test statistic were greater than 1.64. And we know that when H0 is true, Z follows a normal distribution, a standard normal distribution. So what's the probability for a standard normal distribution that Z is greater than 1.64? It's 0.05. So the size of the test in this case is the probability of type 1 error, which is 0.05. And sometimes this is referred to as the significance level. So significance level is the probability of type 1 error in this case. Okay, so that is in some sense a basic discussion of the theory of hypothesis testing. There's a lot more that we're going to mention, and the first thing we mention very briefly is what happens if sigma is unknown. Well, as I said, we aren't going to dwell on this, but what happens when sigma is unknown is that the above standard normal distribution becomes a t distribution. With an appropriate number of degrees of freedom. So the ideas that we've met about rejecting the null hypothesis when the value of the test statistic is in the tail go through in the same way, except we estimate sigma, so we have to estimate it, and because of that the distribution of the test statistic is no longer standard normal but is a t distribution. Okay. So now we're going to talk about the p-value. So the p-value is something that's given to us very often by a computer program, and it's something that very often people find quite difficult to understand what it means, but we'll just try and go through it again using the picture that we've had before. So here's the standard normal distribution. So maybe I'll write this as normal 0.1. Here's the values of the test statistic. And this would be the distribution of the test statistic if mu equals 3. And we've seen this idea before, that we have a cutoff value, a critical value 1.64. And within the tail here, we have evidence against the null hypothesis in favour of H1. And we've called this region here that's cut off by the tail the critical region. And we've seen that our rule is in the critical region we reject H0 because we have a sufficiently rare value under the null hypothesis, and below the critical region we do not reject H0. Okay, so our value that we looked at in our example above was 2. So we had a value of 2. So that means for that value, when we observe 2, we reject H0, and therefore we conclude that mu is greater than 3. So that's the conclusion that we would reach when we observe 2. The p-value is the area, in this case, to the right of the value of the test statistic that we observe. So the p-value is the shaded area all the way up to infinity. So to put it more formally, the area that's more extreme than the observed value is referred to as the p-value. Okay, so in this case, by more extreme than the observed value, I mean in the direction of the alternative hypothesis. So more extreme values would be in this direction, because in this direction we're gaining more evidence in favour of the alternative hypothesis. So the area more extreme, and I think we should more correctly say in the direction of the alternative hypothesis. Another way to think about the p-value is that the p-value quantifies how rare the observed value is. So here the observed value is 2. You can see that the p-value quantifies that in the sense that the p-value is going to be small. It's certainly going to be less than 5%, because we know the whole of the area above 1.64 is 5%. So the p-value is going to be a small number, and it's a quantification of how rare the observed value is if the null hypothesis is true. So another way of writing the p-value is that in this case it would be the probability z is greater than the observed value, given that conditional on the null hypothesis being true. So that's another way of thinking about the p-value. Okay. Now, what's the use of the p-value? Why do people talk a lot about p-values? Well, one of the reasons why the p-value is used is that the p-value would be given to us by a computer. So when you do a test, not just the test we're doing now, but any test on a computer, the computer will give you back a p-value, and then you use your p-value to make a decision about the hypotheses. So let's look at the two cases. Let's look at the case when H0 is rejected. So this will be represented by this diagram here. So again, we have Z and the standard normal distribution that represents Z. And here's 1.64. We cut off 5% in the tail. And we're assuming in this case that H0 is rejected. So this means that we've got a value up here. Our value of Z must be in the tail, because this is the part of the critical region where we reject the null hypothesis. So this means that if we work out the p-value here, maybe I'll shade that in blue, the p-value will be less than 0.05. Because you can see that the area that defines the p-value, the one I've shaded blue, is less than the 5%, which I'm now going to shade in green. So the p-value is less than 0.05. So when h0 is rejected, the p-value will be less than the size of the test. If we look at the other possibility, when h0 is not rejected, so a different possibility, we've got the same picture. So this is the distribution of the test statistic under the null hypothesis. We have the 1.64, again cutting off the 5% in the tail. We have our rejection or critical region here. But we're now in a situation where we aren't rejecting the null hypothesis, so our value must be less than 1.64. So that's the value we observe. It's not in the critical region, it's not in the rejection of the null hypothesis region. And when we work out the p-value associated with that, it's going to be the whole of this area, now shading in blue, above the value that we observed, and our p-value is clearly going to be greater than 0.05. So what we have in this case is a rule, and the rule says that if the p-value is less than 0.05, or in general is less than the size of the test, we reject the null hypothesis. And that's how we use a p-value given to us by a computer program. And that's what a p-value is. Okay. Now, talking before about errors. So one of the errors that we discussed was the type 1 error. And the type 1 error was the probability, the type 1 error was reject h0 when it's true. So an error is the act of rejecting h0 when it's true. In this case, the type 2 error is defined in a similar but different way. The type 2 error is that we do not reject h0 when it's false. So type 2 error is about not rejecting a false null hypothesis. So h0 is false. Now if h0 is false, then of course that means h1 is true. And in this case, h1 is true means that mu is greater than 3. So the alternative hypothesis can be true in many, many different ways, an infinity of different ways, because it can be true whenever mu is greater than 3. And this allows us to perform a more complicated calculation to work out the probability of type 2 error. So that's what we're now going to go through in detail. So the probability of type 2 error, the probability that we make this different error, is the probability that we do not reject h0, given that h0 is false. So that's the probability that we do not reject h0, given that, well, how can h0 be false? Mu takes a value greater than 3. So to write that in a slightly shorter way, that's the probability we do not reject h naught given mu equals mu1, where mu1 is greater than 3. So why am I using the 1 here? Because I'm indicating here a value allowed under the null hypothesis. Sorry, under the alternative hypothesis for the 1. Okay, now we can work out what that probability is. So that's the probability of do not reject h naught. When do we not reject h naught? When z is less than 1.64, conditional on mu being mu1. Okay, so I think I'll now move on to the next page and work out what that probability is with a little bit more space. So we're now working out the probability that z is less than 1.64, given that mu is equal to mu1. And that's equal to the probability that the test statistic x bar minus 3 over sigma over root n, the standardized difference between the mean and the sample mean and the postulated mean, is less than 1.64 given mu equals mu1. Now, the only thing that's random here that we do not know is x bar, the sample mean of the data. So let's isolate that. So we've got the probability that x bar minus 3 is less than 1.64 sigma over root n, given that the true value of mu is mu1, where mu1 is greater than 3, and that's equal to the probability that x bar is less than 3 plus 1.64 sigma over root n, given mu equals mu1. Now, does that help us? Well, it does, because we have now got x bar as, if you like, the subject of this. But what do we know about x bar? We know that x bar follows a normal distribution with mean mu1 and variance sigma squared over n. Why do we know that? Well, we've already worked out what the distribution of x bar is, and we know here we're conditioning on the fact, we're assuming the fact that the sample mean is here, sorry, that the underlying random variable mean mu is mu1. So we're actually making use of that assumption. X bar is normally distributed with mean mu1 and variance sigma squared over n. So we can now perform standardization here. So the first thing when we do standardization is we subtract the mean. So we have x bar minus mu1 is less than 3 plus 1.64 sigma over root n minus mu1, all conditional on the fact that the true underlying mean is mu1. And then we standardize by dividing through by the standard deviation. So that's just x bar minus mu over sigma over root n, sorry, mu1 is less than 3 plus 1.64 sigma over root n minus mu1 divided by sigma over root n, given that mu equals mu1. Well, at that point we can be quite happy, because we know that when we perform that standardization, when we subtract the mean and divide through by the standard deviation, that becomes a standard normal random variable. That's what we saw earlier. So this is just the probability that a standard normal random variable is less than that quantity. And I'm just going to write the quantity by putting the mu and the 3 together. because they're both sort of means, 3 minus mu1 plus 1.64 sigma over root n, all divided by sigma over root n. Well, I can work out now this probability using a computer, because the probability that a standard normal is less than a particular quantity can be found using big phi, which in R is given by P0. So what I've actually achieved by this is that I've achieved that the probability that I do not reject H0 given H0 is false, and let's remind ourselves that that's the probability of type 1 error, beg your pardon, type 2 error, is equal to big phi of 3 minus mu1 plus 1.64 sigma over root n divided by, all divided by, sigma over root n. And that is when mu1 is a value compatible with the alternative hypothesis, namely mu1 is greater than 3. So what we've done above is the calculation of the probability of type 1 error. And this is very much related to the idea of power. And power is a very important idea. Very often if you're working with a client or a medic or a scientist, the discussion will turn to a power calculation. And let's now define what power is. Power is the probability that we reject a false null hypothesis. So power is the probability that we reject H0 when we should reject it. So it's the probability we get something right in the sense of rejecting a false null hypothesis. Well, that's easy to work out now, because that is 1 minus the probability that we do not reject H0, given H0 is false. That's just using complementary probabilities. Probability of A is 1 minus the probability of not A. And we've got a formula for that probability above. So that's 1 minus phi of 3 minus mu1 plus the other quantities that we've written before. Now, it's interesting that if we plotted this power on a graph as a function of mu1, so here we have power as a function of mu1. Here we have mu1. We know mu1 is greater than 3. So here is 3. Power is a probability, so it takes values between 0 and 1. So here's the 1 going up here. Here's 3. So if we plotted power as a function of mu1, and I'll just show you where mu1 appears, there's mu1, then that looks something like this. So it goes up and it tends up to 1. So the power increases the further out you go in the null hypothesis. Sorry, the alternative. So the power increases the further you go in the alternative hypothesis. Remember, the alternative is mu is greater than 3. So we're going further and further into the alternative hypothesis as we go along this axis, and the power increases. And that's a good thing and a sensible thing. It means further the truth is away from the boundary of 3, the more likely you are to reject a false null hypothesis. It actually turns out that this value of the power at 3 is 0.05, which is the size, and you may like to think about why that should be the case. So that's a graph of the power against mu1, and we can actually produce another graph, because the power, which we've written above, I'll write it again, is the probability we reject H0 given H0 is false. We've seen that takes the form 1 minus phi 3 minus mu1 plus 1.64 sigma over root n over sigma over root n. And this clearly depends on the sample size n. There it is, occurring twice in that formula. Now, we can now plot the power as a function of n. So here's the sample size n. Here's power as a function of sample size n. We know power lives between 0 and 1. N is obviously increasing along this axis. And so here's 1. And it turns out that power increases as sample size increases. So power increases to 1, goes up to 1 as the sample size increases. Okay, so what may happen in practice is that a client comes along and says, well, I want to know the sample size that achieves a power of 0.8, for example. So here's a 0.8. By the way, this graph is for fixed value of mu1. So here's 0.8. You'd look along here. You read off from the graph the value of n. And then you'd say to your client, well, I can guarantee that you have a power of 0.8 or more, provided you have a sample size for your experiment of that value there or more. So that's exactly what the clients very often ask for. So the client specifies a power, for example, 0.8 at a given value of mu. So what the client is requiring is that the probability that he or she rejects H0 given H0 false equals 0.8. So the client is specifying a required property of the test, and what you're being asked to do in that case is solve the equation that we've got above. This equation here, we're being asked to solve that for values of n. Find the sample size such that this equation holds. So we're being asked to solve this for n. And usually that is solved numerically, and you don't usually get an integer value for sample size, but then you just use a sample size that's greater than the value that you obtain when you solve this equation. So that's an example of a very important technique which is referred to as a power calculation. Okay. So we're nearly at our end of our journey, our discussion of hypothesis tests. I just want to say something at the end about two-tailed tests. Now, the test that we've been working with up to now has been a one-tailed test. So we've been looking at the example of testing mu is less than 3 against the alternative that mu is greater than 3. A different set of hypotheses could test whether mu equals 3 against whether mu does not equal 3. And if we look at the alternative hypothesis there, that splits up into mu less than 3 and mu greater than 3. How is mu different from 3? It could be less than 3 or it could be greater than 3. And this one is referred to as a one-tailed test. And this is referred to as a two-tailed test. Sorry, a two-tailed test. And when we drew our picture of the critical region for the one-tailed test, it indeed had one tail. So here we had z, here we had phi of z, the distribution of the test statistic under the null hypothesis. And what we did is we said we'll cut off 5% in this tail, corresponding to mu greater than 3, and that's cut off by 1.64, and in this part we reject h0. So this is the critical region for the one-tailed test. When we've got the two-tailed test, then what happens? Well, we proceed in a similar way, but we've got these two tails of the alternative, and so what we do is we cut off 2.5% in each tail. So here it is 2.5% in the upper tail, and that's coming from the mu greater than 3 part, which we've seen before. Here's the 2.5% in the lower tail, and that's coming from the mu less than 3 part. The values that do that cutoff are approximately 1.96 and minus 1.96, and this is the critical region is divided into two parts. Here and here we reject h0. In between, we would not reject h0. So also here in this diagram we do not reject h0. So that's the essential difference between the two-tailed and the one-tailed test. One-tailed test has one tail, and the two-tailed test has two tails in the alternative. That means we have to define our critical region in this way into two disjoint pieces. And this makes life a little more complicated. So when we talk about the definitions of p-value, or when we work out the probability of type 1 error, or when we work out the probability of type 2 error, or when we work out the power, we have to remember to take into account the fact that our test procedure is defined using not one but two tails. So that means formulas get a little bit more tricky, but not impossibly so. So that is the end of the material I want to present in this podcast. What we've looked at today is the theory of hypothesis testing. We haven't looked at a range of different statistical tests, but we've concentrated on one, and we've tried to get out some of the underlying theory about this. We've looked at some motivation for the choice of the test statistic. We've looked at some distributional theory to define a critical region. We've defined the idea of size or significance level. We've looked at type 1 and type 2 errors and their associated probabilities. And we've also looked at the important idea of the power. So thank you very much indeed for listening, and I hope that you found this podcast useful.